sample that we didn't get a chance to cover in class. In this one, we are basically going to be creating that consolidation curve from scratch. So following very similarly to how you would measuring all of the mass and measuring the heights of the sample over time in the consolidometer, and then finding that E or void ratio, and then the log pressure curve that's used for your consolidation curve. So we're given the diameter of our specimen or our sample. Remember, think of that like little hockey puck of clay. We have the initial height of the specimen, and then the specific gravity of the solids and the mass of the specimen, the dry mass. Remember, just as some insight to specific gravity and the dry mass, these are usually calculated or determined after the fact. So, you know, you go through all of this whole experimentation process and then do some additional tests at the end to then back calculate all of these values that we're going to be finding. We're also given the data here from the pressure, increasing by 2 each time, and then the resulting dial gauge. So this dial gauge is showing the essential deformation of that. So our initial, is going to be 0. And then as we add the 500 pounds or 500 PSF, and we have this increasing deformation. So the first step here is going to be finding the volume of the solid portion only. So for the volume of the solid portion only, we have the dry mass of solid, and then the density of our solid. And we know that this is equal to the volume of our solid. So this is going way, way back to elementary school or whenever we learned this, our density triangle. That looks like this, our DMV triangle. We need to find the velocity, so that's the mass over the density. Now, density in this case, since we are in SI units, that's just going to be equal to the specific gravity, assuming the density of water is 1 gram per cubic centimeter. So we'll plug stuff in here. We have our mass of solid of grams here, and then of course our specific gravity times the density of water, meaning that our density of our solids is 2.72 grams per cubic centimeter. This means our volume of solid is going to equal 27.91 cubic centimeters. So this is just the solid portion of our clay sample. Next, what we need to do is find our initial void, or the initial total volume. So remember here that like we're talking about this like little sample hockey puck of clay that's taken from our Shelby tube. And we're given the diameter of this sample of 2.5 inches. And we're also given the initial height of our specimen, that's being 0.78 inches. So we can find our total initial volume. It's just the volume of this cylinder. So pi r squared times that height, or the initial height. And when we calculate this out, we get 3.83 cubic inches. I'm going to go ahead and just switch this over to cubic centimeters as well, because we will have to go back using cubic centimeters. So equal to these two. So next we'll find our initial volume of the void. So for the initial volume of voids, we know that our total volume, or the one that we just found, is going to be our initial volume. And with our phase diagram, we have a volume of solid, and we also have a volume of void. So that's going to be what that makes up. So therefore, we can rearrange this equation to solve for the volume of voids, meaning that this is the initial volume minus that volume of solid that we found earlier. So kind of straightforward, our initial volume of voids, so I'm just going to put this subscript 0 for the initial standpoint. This is going to be 62.74 minus 27.91, or not 38, 34.83 cubic centimeters. All right, the next step will be finding our initial void ratio. Remember, void ratio is going to equal the volume of voids divided by the volume of solids. So for our initial void ratio, This is going to be the initial volume of voids over our volume of solid. Remember, that volume of solid is not going to change at all over this time. We're going to assume that the volume of our solid portion is not actually leaving the oedometer, it's not getting washed out or anything. The pervious stones are going to be locking that all in to that sample. So here we're using this in cubic centimeters. So cubic centimeters over cubic centimeters, this is our void ratio, equal to 1.248. And that's our initial void ratio. So what we'll do with this next step, we can start developing or determining this void ratio for each one of these pressure curves. So the main thing is going to be finding this void ratio that goes along with each one of these pressure values that we have here. So what we first need to do in this step, and I probably should have done this a while ago, I'll change it to blue here. We need to determine the height of the solid material. This is that height of solids. And since we're given the volume and we know the cross-sectional area, again, kind of simplifying this into like a 3D phase diagram. You know, technically this sample is going to be water and then solid portion. So we have this height of solid and then that height of void here, that's going to be filled with water. So we need to find that height of section. So the height of the solid section is going to be equal to the volume divided by that cross-sectional area. So the volume is going to be 2791 cubic centimeters. The cross-sectional area will be pi r squared. So that'll be what, 2.5. This is in inches though. So we need to convert this over correctly. And so for the height of solid, what we'll get is 0.881 centimeters. Remember that, 2.54 centimeters is equal to 1 inch. So we need to make that conversion here. So once we find this height of the solid, we need to find the change in void ratio each time. So remember, this height of solid here this does not change through the entire test analysis. We're assuming this is not changing. So what we need to do next is find that change in void ratio. And if our change in void ratio is going to be the change in the volume of voids divided by the volume of solid, but then knowing that this volume is going to have the same cross-sectional area, then this change in volume of voids is really just the change in height of our change of height of our volume of voids divided by, change in height, I guess, just change in height divided by the, multiplied by the cross-sectional area. And then this would be the change in height of our change of height of our solids, which is not changing times the area. So the areas cancel out, and our change in void ratio can essentially be boiled down to the change of height divided by the original height of solids. So this is where we would have to start looking at this dial gauge. This is going to essentially be the change in height. This is in inches though, so we would need to ensure that we put this into centimeters. So we would look at this change in height here. This would be equal to 0.0401. And then we would also calculate the change in height each time, so due to each incremental load. So when we have our change in height, we can find our change in void ratio by plugging that in and keeping the volume of solid constant or height of solid constant. So change in height or change in void ratio in this first case. So I'll just put this as 1. This is going to be 0.0401 centimeters divided by our height of solids, which is 0.881 centimeters. So this is going to lock in here, and our change of void ratio is going to be 0.046. So that's for our first step. We would then do find the new void ratio, or in this case, we'll call this E1. So E1 is going to equal E naught minus the change in void ratio. This is equal to 1.248 minus 0.046. And so our new void ratio will be 1.202. So essentially what we're saying here is 4. So if we're looking at Cartesian points of our plot, the x-axis would equal 500 PSF, and our y would equal our void ratio of 1.02. And then you would do these all the way for each one of the x values. So this is actually what we're looking at here when we want to plot this. You can see here, this is the deformation in inches that we were just showing before. We see the change in thickness and then the change in void ratio and then this new associated void ratio here. So what we're actually plotting would be this void ratio on the y-axis and then this pressure here on the x-axis. And so if we plot that, it looks kind of funky at first. Again, this being x and this being our y. But what you may note is down here, we need to ensure that this is in a log scale. And when we put this in the log scale, we see a clear trend of our consolidation. And so with this, then these discrete data points, you would then use some type of fitting tool to fit these. And then you would hopefully have a little bit more clear trend of our C, and then the CR or CS. You could also then use the Casa Grande technique to find our pre-consolidation pressure like we talked about in class.